Okay. Hi everyone, good afternoon. Thank you all for joining us today at another Compass Wednesday. Today I'm here to introduce Nathanaël Dossa. He's a postdoc here at Rosenstiel School in the Beal Lab, studying sub-mesoscale dynamics in the Agulhas leakage region. His academic journey began with a bachelor's degree in physics from the University of Abomi Calavi in Benin. He then earned a master's degree in physical oceanography from the University of Paul Sabatier in France, followed by a PhD in physical oceanography from the Federal University of Pernambuco in Brazil. His doctoral research focused on near-surface ocean dynamics off of northeast Brazil and global coastal sea surface salinity gradients. After completing his PhD, he undertook a postdoc in Brazil, further advancing his research. He's also had the privilege of visiting Woods Hole and Scripps as guest investigators, where he explored key aspects of ocean salinity and sub-mesoscale dynamics. Outside of all of his physical oceanography work, he enjoys playing soccer, watching movies, and reading books. Today, he is discussing one of his previous bodies of work on coastal salinity gradients. Take it away.
Okay, thank you, Paloma, for this brief introduction. I think you said everything about me. So, yeah, as she said, I'm Nathanaël Dossa. It is a pleasure for me to be here and discuss about oceanography. So, this afternoon, I will discuss global analysis of coastal gradient of sea surface salinity, which is one of my previous work. So, yeah, why do we study coastal sea surface salinity gradient? As we all know, sea surface salinity is an important parameter for is an important climate variable which play a key role in the ocean-atmosphere interface where most flushes occurs. As you can see from this movie, sea surface salinity at global scale is mostly driven by the balance between evaporation and precipitation. For instance, we can see from this movie that in subtropical gyres we have the high sea surface salinity, because in this region the evaporation is higher than precipitation. In intertropical convergence zone, the salinity value are lower compared to subtropical, and we can also see that in some coastal region, like here in the region of Amazon plume, we have a low value of sea surface salinity. At high latitude, we also have a low value of sea surface salinity because of the dynamic of sea ice. The sea ice content of salt is lower than the seawater salt content. So salinity does not only play a key role in the ocean atmosphere interaction. It's controlled with the temperature, the seawater density, so that we have a high sea surface temperature on the freezing sea ice will contribute to the deep convection, which is a key trigger for the thermosalinography circulation, which play a key role in global climate. Low salinity induced by precipitation and river runoff creates stratification, and this stratification can lead to what we call the barrier layer. You have the mist layer here at the top, and you have a strong stratification induced by river runoff and precipitation. And within an isothermal layer, you have this stratification, and this layer is called barrier layer. And when barrier layer occurs, It limits the exchange between the ocean and the atmosphere and enhance interaction between the ocean. I mean, it actually limits the exchange between the ocean surface and the deep ocean, which enhance the interaction between the ocean and the atmosphere. In the coastal region, sea surface salinity can bear the signature of different processes. The first is the discharge of river runoff. As you can see here, we have Amazon plume. Due to its discharge, we have low salinity value. And the dynamic here in this region, I will come on it later. We have North Brazilian current, which retroflects, and from the retroflexion, we have North Brazil current rings. So the dynamic along this code transports the low salinity value to the open ocean. In tropical region, it has been recently shown that the rainfall is much more concentrated in the coastal belt within 100 kilometers, and the input of this rain is comparable to the river discharge. So we have in the coastal region, river discharge, you have important precipitation in the coastal belt, which can lead to the salinity decrease in the coastal region. In addition to that, we also have coastal upwelling. Actually, what we know, I mean, our basic knowledge is when coastal upwelling occurs, it uplifts the fresh water to the surface. But in some region, due to the depth where this upwelling occurs, it can advect the high salinity water to the surface and generate sea surface salinity anomalies, which is shaped by the local Rossby ridges deformation. And all these anomalies that occur in the coastal region are mostly redistributed to the open ocean by a longshore current. So, in order to understand, I mean, the salinity at the global scale, many efforts were made. In addition to traditional CTD casts and bottle sampling, ArgoFloat were launched, as you can see here, distribution of the ArgoFloat. This ArgoFloat collects temperature and salinity profile at the various depths. There were also thermosalinography, TSD, which are installed on voluntary observing ship across the global ocean to acquire the salinity and temperature in the first 10 meters. Here is an example of the trajectory of a voluntary ship crossing the ocean, and this is managed by a French network. And we also, much more recently, satellites were launched to monitor sea surface salinity. We first have a satellite Soil Moisture Ocean Salinity, SMOS, which was first launched, and then Aquarius, which was replaced later by SMAP. These satellites data and in-situ data altogether combine to monitor, to study the salinity at the global scales, and also with a numerical model help us to understand the salinity distribution at temporal and spatial scale. But when it comes to coastal region, the sea surface salinity pattern and its gradient remain poorly documented because of three main reasons. The first is because our coastal in situ data are relatively sparse, both in time and space. The continental freshwater foxing and its incorporation to numerical model is is challenging, and it needs to be refined. Satellites in coastal region have a limitation because when the salinity satellite, when it moves from the land to the continent, the change of region of different property, this change from the land to the continent lead to some bias in the data, and also in some coastal region like in European, Asia, and the Middle East, we have a radio frequency interference that induce bias in satellite data. So in this context, our current study here is aimed to compare satellite products that we have and reanalysis models. Compare this data with in-situ thermosalinography observation in a coastal region in order to quantify the skills of this product. So we will use the thermosalinography data at the global scale, but we'll focus on the the 300 kilometers from the coast. From the coast. We'll use the thermosalinography data. Thermosalinograph are installed on the voluntary observing ship and research vessels. Here is the global distribution of this data from the coast of 300 kilometers from 1993 to 2019. We compare this data with four products. Actually, SMOS and SMAP data are processed in 4 different centers. We have a SMOS, the product SMOS called SMOS Ocean, which is processed in l'Océan, which is French laboratory. And the same data is also processed in Spain from Barcelona Expertise Center. And SMAP data are processed with the people of JPL, Jet Population Laboratory, and Remote Sensing Service. In addition to this data, we will use the reanalysis, which is a combination of satellite and not actually satellite and in-situ measurement. So first what we did is we estimate the gradient of sea surface salinity. This is from in-situ data. What we do, as we have a different ship crossing the ocean, we will extract the cross-shore section, the cross-shore track of every ship trip. First, we take a single ship trip. This is an example for a cruise. Other ships can have like a long shore or cross shore. This is an example. What we do is we first, from this single trip, we extract the transect that are perpendicular to the coast, like here, and along each transect, we estimate the gradient by using linear feet along, like supposing that this blue line is the ship track, is the distribution of sea surface salinity along the ship track that we extracted as a cross-shore section. We will linearize the salinity distribution with linear feet to have the gradient, so that the salinity, the positive gradient will be salinity increase at the coast, and the negative gradient will be salinity decrease at the coast. And we repeat this for every ship transit crossing the global ocean. From gridded data, the way to estimate the crusher gradient is different because data are gridded. So what we do here is here is the distribution of the gridded data. For each 25 kilometers along the coast, we computed the cross-shore section as this black line here, and within a rectangular around this section, we interpolated the gridded data along the cross-shore section as the red dot here. And from each cross-shore, we now use again linear feet to estimate the gradient along each section at the global scale. To perform the comparison between the thermosalinograph and the in-situ, we collocated the gradient estimated from the salinity and the gridded product, both in time and space. So imagine we have a gradient estimated along this cross section. We will look to the cross section from the in-situ data within 50 kilometers and compare the gradient from this along this cross section and the gradient estimated from the in-situ section, this in time and space. So first, we look to the salinity, we look to the statistic in terms of sea surface salinity. Here is the bias, actually the difference, the mean difference between the gridded satellites and the reanalysis product and the in-situ. What we did is for each coastal band, 0.50, 0.50 kilometers, 50, 100, 150, 100 and 150, we estimated the bias between both type of data. As you can see, when we are closer to the coast, most products here have a higher bias and higher standard deviation, which is how the difference between products varies. And this is because the performance of the satellite here, SMOS, l'Océan, Berg, SMAP, JPL, and SMAP are SSS. They don't have they don't have a good quality of data. That's why we have the higher bias and higher standard deviation in the near coastal region. But when we go further, like 100 to 300 kilometers, the bias is lower, and the standard deviation also is lower, meaning that there is still an improvement to make in the near coastal region. Further, we will focus before estimating the statistic on the gradient of sea surface salinity. We will focus on different area, and this different area portrays the signature, I mean the sea surface gradient of different sign. First, we look to the region of Amazon River plume, where we have a river discharge. So we expect the negative gradient, meaning salinity decrease at the coast, and in this region, what we have North Brazilian currents, which flow northward along the coast and retroflate eastward. And this is we can see this pattern on the reanalysis data called GLORIS here, where we have the low salinity pattern, which is retroflecting here, and you have the signature here of North Brazilian rings. So when we compare, I mean, if our satellites do reproduce what our in-situ is showing, we can notice that satellite products, all the satellite products here show the salinity decrease at the coast, but they fail to, I mean, they fail to show this offshore, I mean, this distribution offshore of the lower salinity along this transit. Maybe because we hear the ship, I mean, this transit was from March 6th to 9th, and what we are comparing here is actually is the same date of data, but the thermosalinography here was acquired in the first 5-10 meters, while satellite products are in a very in the first centimeters of the ocean. And also the resolution of this satellite data actually an average of 8 mean composites, so that may be why these data don't really reproduce what really occur along this transit. Another region of example to characterize the coastal gradient is the region of northeast of Brazil, where we have a strong evaporation along the coast. And we also have North Brazilian undercurrent, which have a salty core. And what happens is sometimes this current rises to the surface with its salty core and could induce positive gradient. I mean, salinity increase at the coast. And here, all products represent well this high salinity at the coast. But we have a SMAP that here have some flagging data, and might be the reason why we have like an suspicious decrease here. But once again, the products here generally show that in this region we can expect salinity increase. Another example is the region of the Great Australian Bights, where we have what we call an inverse estuary. An inverse estuary are a region where we have a strong evaporation and salinity increase toward the estuary. In this region here, we can see that at the coast we have salinity increase from the in-situ, and this salinity increase expected in this region is well shown in GLORIS data, and you can see that GLORIS here has data in the Gulf Spencer here called inverse estuary. But other products like SMOS bag, SMOS bag for instance show an increase, salinity increase in the Gulf. Once again, the salinity increase at the coast is shown, but SMAP, two SMAP products don't really have they don't have I mean, here they remove a lot of data so that we don't have data in the Gulf, but we can see that they show the salinity increase. GPL here doesn't have a lot of data, but it does reproduce here the salinity increase. So these are, I mean, three key examples that portray salinity pattern, showing that different process can induce salinity, different salinity pattern at the coast. First, we now look to the gradient. I mean, the salinity gradient estimated along cross section. Here is the gradient estimated along the section from 50 to 250 kilometers. We collocated thermosalinograph in each product, and as you can see here, we have a salinity, I mean, positive gradient of northeast of Brazil that is shown by SMOS l'Océan, SMAP GPL, but we have some negative here that appears. Gloris also reproduce well this positive salinity of northeast of Brazil. In the plume of Amazon River, where we expect the negative gradient, we can see that all products reproduce this negative gradient except SMAP SSS, which shown a positive, contrary to negative gradient. And this may be due to, I mean, maybe the number of cross-section average from in-situ data compared to SMAP SSS. When we look to the global distribution of the collocated gradient, we can notice that the distribution of the gradient seek toward negative value, showing that at the coast we have much more freshening, and due to the tropical rain and coastal river discharge. But when we have from this, which of the product is the best in estimating the cross-shore gradient, we can say that the Gloris here in the SMAP GPL, which succeeded to show some key example of gradient, and also these two products have a good standard deviation when we compare to the in-situ data. When we look to, I mean, the statistic in terms of the gradient, compare the gradient of the same sign by collocating a gradient in space and in time. Here, first, what we did is we looked to the gradient of same sign collocated in time and in space, and we can say that all products here fail in estimating the sign of the gradient in the proportion, I mean, 30% of, the product failed to estimate the gradient in proportion higher to 30%. But in terms of the bias in estimating the gradient, we can see that the statistic, I mean the gradient statistic here is different from what we observe from the salinity bias. So we don't have any relation between the bias in the salinity and its cross-shore gradient. So what can, I mean, among the all products compared to the in situ data, what could be the best product? We can base our analysis on the product that have a mean standard deviation, lower standard deviation and lower bias. When we look to SMAP JPL, we can see that the bias from JPL is lower. I mean, is smaller compared to other product, and its standard deviation also in average is also lower compared to others. And in terms of the gradient of same sign, he also has good performance. So SMAP JPL appears to be the best product. Using the same criteria, we have the second SMAP, RSSS, which also show particular same statistic, and then followed by other products like SMOS, Gloris, SMOS. But once again, if it comes to at global scale, SMAP GPL appears to be the best product. But when it comes to use this product, I mean, the user needs to do much more analysis, like on a specific region. Oops. Here, what we did is we looked to the mean, the average at the common period of the gradient estimated from each product. But here I'm showing Gloris and SMAP GPL. As you can see, Gloris here perform better compared to GPL, even though GPL seems to be the best. Gloris, because has much more data at the coast. It's showing here the salinity increase of northeast of Brazil and in the Greater Australian bight. Salinity decrease in the Amazon plume, where here GPL failed to reproduce. So even though this product is the best, it does not really reproduce the key features in some specific region. Yeah, that's all for my talk. To conclude, we can return that satellites reveal the dominance of coastal freshening, which is related to the river runoff and tropical precipitation. The satellites products, their skill here are very dependent, and for specific use of this data, it needs to go through specific validation. but SMOS here appear to be the best product in estimating the coastal sea surface gradient. But however, there is a need to have the higher resolution of SMOS data. Okay, thank you.
Thank you, Nate, for your talk. We'll now welcome any questions from the in-person audience first, and then we'll go to Zoom. Paquita?
So you show a lot of features with the reanalysis that doesn't show up in the satellite products, but I would think the reanalysis is mainly depending on the satellite for data assimilation. So where is it getting its additional information from? Like off of Brazil, you could see that there were two really nicely contoured waves in the reanalysis that you couldn't really see in the satellite imagery.
Okay. Satellite, reanalysis product, the one we use here, first the resolution is higher than the resolution of satellite, is 1/12 degree. And also he has much more data at the nearest coast region. And he simulated, is first with sea level altimetry altimetry data and in-situ data as well. And that may be the reason why satellites fail to show the scale shown by the reanalysis. And also the temporal resolution of the model the reanalysis is 1 day, while the satellites are the composite mean of 8 days.
Okay, thanks.
Do we have any other questions?
Yeah, I can ask some question. My question related to slide where you show the North Pacific Ocean. So can you go back to that slide? I don't remember exactly the number. Further, yeah, keep going. It's a spatial plot. Yeah, here. Yeah. So by seeing this plot itself, I can say that the SMAP JPL product not good at all, because at least the 4 other products kind of consistent. If you see the North Pacific region, and you show this plot, and you show like the global, a lot of coastal regions. So my question is like, really, what is the main goal you want to achieve? Like you study more, suggesting which product is good for the particular region you are studying?
No, actually, these examples are not to show that there is a best product in a specific region. No, to show that one product is good in a specific region, you need to go for the validation. But I wanted to show.
Validation with what?
It has to be compared with in time and in a much more smaller scale with in-situ data. Here is to portray that we have in this region, for instance, we can expect positive gradient like salinity increase at the coast due to the strong evaporation along the coast. This is an example to show that we can expect, different gradients, gradient of different sign from one region to another. But the goal is to show which product is the best at the global scale.
Yeah, so based on this, which one do you think to go, like if you have this product without seeing another analysis, whatever you have done, I would say at least these 4 products are consistent in terms of, if you see, and JPL is kind of outlier.
Yeah.
So I won't consider that. I'll discard from the beginning itself.
Yeah. You can say JPL is not good product, right?
Yes. But the analysis you showed one plot where you rank, I think the JPL and RSS like the first and second.
These are the global scale, but here is for what I'm comparing here is each product with this specific transit to see if, I mean, they can show the salinity increase at the coast, which is expected in this region. GPL failed to show that. I mean, in the month of the Gulf here, you can also see that they remove. They don't have really a lot of data in the coast. But this is not. We cannot say that is not good.
I'm not saying it's like it's bad. I'm just saying by seeing this, it's outlier.
Yeah, comparing here for this specific region, yes. But most products here do show the salinity increase. But when it comes to global scale, JPL appears the best.
Okay. And another question about you compare with something, you compare the bias and also the standard deviation, and you said it's high bias or low bias, and you use some product. What product? The product you generated the data, or is like what is the benchmark on that? From where that data come from? So you remember that? Like these are like
yeah.
What is the reference for that? Like
okay, here what I'm showing here is we estimated the gradient, the threshold gradient from each product and in situ thermosalinograph data.
Okay.
And we collocated both in time and space. If I take, for instance,
collocated based on the TSG or collocated based on what?
Based on TSG.
So that you're considering the best data, right?
Yeah, this is the in situ considered as the best data. This is the reference.
Mm-hmm.
So we estimated the gradient from both, I mean, thermosalinograph and each product. Mm-hmm. And then we collocated in time and space to see what would be the difference. And here, when I take here the gradient estimated, I mean, at 150 kilometers. This is the length of the cross section considered. When we look to this, this coastal band, by collocating in situ and each product, how many gradient? How many pairs do we have? How many pairs do have same sign, like at a date, at one date and same location? Mm-hmm. Do we have the gradient of? Do we have positive gradient from TSG and another product? This is here the percentage. So when we use, if the product show the gradient of the same size with the thermosalinograph and have lower bias and lower standard deviation. The standard deviation here is how this difference between, in terms of gradient, how it varies. When you have higher pairs of gradient of same sign, lower bias, mm-hmm. and lower standard deviation means that
got it.
Yeah, it's better. Yeah.
So is the main metric for how well the satellite product is performing per se just based on how much coastal data there is? Is that basically the only metric you're using to kind of say, hey, this satellite data is actually representative of the salinity gradient or not?
Please
And then just how many data points you have near the coast, like for each of these products?
I don't really understand the question.
So essentially, just is the success of, the satellite product based on how many measurements or like values you have closer to the coast? Is that the only metric you would say is deciding whether it's, representative or not of this gradient?
Yeah, is based on how many. Actually, what people that process this data do is in the coastal we have the satellite sensor have a limitation, and they try to remove bad data. So each year they have try to perform a new algorithm that have to have a lot of good data in the coastal region. When I take this for instance, here what we can, oh no, sorry. Yeah. Here, for instance, this is the bias from the sea surface salinity. In the nearest coastal region here, 0 to 100 kilometers, most products here have higher bias, higher standard deviation, and they have also, we have a higher number of collocated data. The higher bias here means that the difference from the product to the in-situ is higher, meaning that it's not really good. So the best quality here will be based on how many good data do they, how many good data, how many good data do they have in the nearest coastal region, and how this data is closer enough to the thermosalinography data.
All right, do we have any other questions in the audience? Nope. On Zoom?
Igor switched his camera on, but I don't know if you had a question. Igor, do you have a question? No. No, he says no.
No? All right, well, thank you again, Nate, for your talk. Is there compass on Friday?
No, nothing on Friday.
No compass this Friday. We'll see you next Wednesday for another Compass Wednesday talk with our newest OCE faculty member.